Yeah, so hello everyone. So in this video I'll be discussing about the Mason model. So yeah, in one of my previous video, which is the Butterworth Van Dyke model, I had got a request from Anuj Ashok to do a video on Mason model. So then I thought I'll do a video on this. So first so what is Mason model? So before actually going to Mason model, I'll just tell you guys about the analogy between mechanical and electrical, because that is something we will be needing in as we move forward in this video. So 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 whenever you are looking at these resonators, or when you're looking at whether you're looking at a piezoelectric material or you're looking at the conversion of a of one model to another. So analogy is voltage, then displacement you can analogy is charge in electrical. For voltage it is current, sorry, for velocity is current, so velocity. For mass it is induction. For spring constant it is capacitive inverse, it's like 1 by C. And for damping it is resistor. Okay, so those are the analogy. So when I'm so in the Mason model, what happens is you're actually, what you're doing is you're considering a wave propagating in a medium and then modeling it in the terms of force, velocity, and impedance. So here, so if you have a, in electrical you call it the equivalence of voltage, you can take here equivalent analogy is force, and for current you can take it as velocity. And there, if you had resistance, here in the Mason model it will be similar to damping. You will have something called acoustic impedance. Okay, so what is acoustic impedance? Acoustic impedance is, I'll show you, it's the density of the material multiplied by the acoustic velocity. So that gives you the acoustic impedance in the of a material. Yeah, you can also write this as ck by omega, where this is the stiffness, k is the wave number, and omega is the frequency. It is 2 pi omega, like that. And yeah, so if you actually consider a wave propagating in a medium, so if this is the two boundaries I'm applying, this is the two material boundary conditions. Okay, and if you am if so so in this, what do you need to find out? So if so in ultimately what Mason model is, it helps you to model in the terms of force and voltage. I told that, right? So which is similar to the voltage and current model. So current resistor V is equal to IR, right? Similarly you can call it like, so in the same formula you can, so when I move forward, you can see how you get to that. Okay, how you can write in terms of force and voltage. Okay, so force and velocity, sorry. And so if I have a if I have a wave incident here, it gets reflected from this boundary. It also get incident here. So by the way, I have to thank my professor at my department, which is Professor Gayathri Pillai. I'm actually doing this video from her lecture, which she had taught in her course in when at this department. So yeah, so and you have a distance t between the two boundaries, okay, and we're just naming it at z is equal to z1. So I'm just taking it as the z axis, okay, and so we need to find what is the force here, just F1, and what is the force here, is F2. So these two things is what we'll be finding at the end of this video. So you can also see that these incidents, so when you have a force applied here, you will have waves formed here, okay, on this region, okay, and because of this incident and reflected waves inside this, you will get standing waves inside, okay. So how can you write the displacement? You can write in the formula as displacement u is equal to a e raised to minus j k z plus b e raised to j k z, okay. What is this? This is the right traveling, or this wave traveling to the right, okay. Okay, and this is the wave traveling to the left. And then these A and B, this constant depends on the acoustic impedance mismatch at the boundaries, okay. Yeah, those things I'm just saying it, you can look upon that if you want to know more. And yeah, so when I'm solving at z is equal to z1, what is the velocity? The velocity v1 is equal to u1 dot, that is equal to j omega u1. What is that? It is j omega, we have already written, e raised to minus j k z1 plus b e raised to j k z1, okay. At z is equal to z2, the velocity v2 is equal to u2 dot, that is equal to j omega u2, that is equal to j omega a e raised to minus j k z2 plus b e raised to j k z1 z2, okay. So now we have to so you will understand why I'm doing all this. Ultimately, the idea of what I'm doing all this, so I want to convert all of this. So I'll just say it in the beginning so that you'll just get an idea on where we are getting this to, okay. So if I want to find the force, how will I find? Force is equal to area into the stress, right? Stress acting on when you're applying a force, you're creating a standing wave here, right? So what all things you have? You have an area on of the where you are applying, and a stress is there, okay. So once you know these two, you can write a is equal to into the acoustic impedance which I discussed before into the velocity, okay. And then you can write, well, how you can write this as a area into velocity into ck by omega, okay. So from this you will be able to get the so here we are able to relate the force and the velocity, okay. So this is the equation relating those two, okay. So ultimately we are what we are trying to do is we are trying to express this equation in terms of force and velocity from starting from here, okay. And so ultimately we are going to make our model from this, okay. So for that we need to write solve we have to solve for a and b, these two terms, okay. This what is a and what is b, then only we will be able to write the whole equation. So we need to make this into a simple model, like for example you have this voltage, you're applying a voltage, you have a resistor here, okay. You have a resistor here, then you have a resistor here. So for example, if I am applying a voltage across these two, V1, if I am having a voltage, ultimately getting a voltage drop here, then you have R1 here, you have R, so you have another resistor here, so you have R2 here. So ultimately, how do you write this? V1 is equal to the current flowing here, which is I1, and which is, so if you have a current flowing here and current flows here, then you can, this is I2 and this is I1 minus I2. So ultimately you know how to write this: I1 into R plus I1 minus I2 into R in this region, it gives you a voltage. So similarly, in this, like this form, you can write your Mason's model in terms of force and velocity. So so that's ultimately the Mason model. So all we are solving here is be to able to express the whole equation in terms of force and velocity and acoustic impedance, so that you can make this model. Okay, this what I'm showing here is simple model. You will need to apply it for other models also, for much bigger models of your resonators, whatever you're doing. So yeah, you need to solve for A and B in terms of uh, V1 and V2. So my first, so this is my first equation, this is my second equation. So first equation, I'm multiplying it by e raised to j k z2, this v1 e raised to j k z2 is equal to j omega a e raised to minus j k z1 minus z2 plus j omega b e raised to j k z1 plus z2. Okay, then as you know before, I had shown here, I can show here. So this is z1, this is z2. So what is the distance? z2 minus z1 is ds z2 minus z1. Okay, so if I can substitute it here, what do we get? J omega, and I bring this side, j omega a e raised to j k d is equal to v1 e raised to j k z2 minus j omega b e raised to j k z1 plus z2. So you can take a third equation, because I need to solve it a bit more so that you can express a1 and a2 in terms of v1 and v2. That's what we need. So second equation, which is this equation, which is this one, so I've written here. So this equation, you can multiply it by e raised to. So I am multiplying it this so that I can get in terms. So these are simple max. You can just try it yourself. So v2 e raised to minus j k z2 is equal to j omega a e raised to minus 2 j k z2 plus j omega b. Okay, so then you can write j omega b is equal to v2 e raised to minus j k z2 minus j omega a e raised to minus 2 j k z2. Okay, so I can write it as the fourth equation. Okay, so substituting for equation 4 and 3, can write j omega a e raised to j k d is equal to v1 e raised to j k z2 minus v2 e raised to minus j k z2 minus j omega a e raised to minus 2 j k z2 e raised to j k z1 plus z2 is equal to v1 e raised to j k z2 minus v2 e raised to j k z1 plus j omega a e raised to j k z1 minus z2. So similarly I can write here z2 minus z1 is equal to d. So yeah, if I substitute that here, I will get v1 e raised to j k z2 minus v2 e raised to j k z1 plus j omega a e raised to minus j k t. So I take it here, j omega a e raised to j k d minus e raised to, I am bringing this side, okay, is to minus j k d is equal to v1 e raised to j k z2 minus v2 e raised to j k z1. So j omega a is equal to v1 e raised to j. So each integral term I am able to express now in terms of both the velocities, okay, which is v1 and v2. Able to express a like this, so divided by 2j sine kd. So this thing, this you know, right? So you can bring this here, and that's how you get the sine term here, okay. And so then similarly, this you can solve for. Similarly, you will get j omega b is equal, when you solve, you will get v2 e raised to minus jk z1 minus v1 e raised to minus jk z2 divided by 2j sine kd, okay. So here so as I told before, this part I will be explaining in terms of, or this applies to anything. So it can be a piezoelectric material, it can be non-piezoelectric material. So if I'm looking at only a simple material which is not piezoelectric, then I can write that the stress is equal to C into which is the stiffness into strain, which is dou u by dou z, okay. And so ultimately, so from this I will be able to write, so force I written before, right? Force is equal to area into stress, so C, which is the stiffness, into the strain, dou u by dou z, strain in the z direction ultimately, okay. So force I can write as j k c a. So where do I go it from? So here you know that u is equal to, so we have solved it before also, that just go, just right. So u is equal, we know we have written displacement in terms of the forward propagating wave and the left or right propagating and left traveling wave, okay. So a e raised to minus j k z plus b e raised to j k z, okay. So if you are differentiating dou u by dou z here, then you will be able to write this. So yes, f is equal to, so ultimately you're differentiating dou u by dou z and then substituting here, you can write jk ca a raised to e raised to j k z minus b e raised to j k z, okay. So as I had shown before, you can write the impedance. So impedance, from here you can go, and so impedance I have written here is c k by omega, or even little bit before also I've shown here. So here, this is acoustic impedance formula, right? So from here you can write this in terms of impedance. So you can write it as jz into j omega a e raised to minus j k z minus j omega b e raised to, so here there is a minus, sorry, I missed here, raised to j k z. Okay, and z as I discussed here, right? C k a by omega k a by omega. So you as I told you, you will have a doubt here. So this is the impedance per unit area. Okay, so which are shown here is actually the acoustic impedance per unit area. So here if you want to, the actual impedance is ckA by omega. That's how you substitute here. Okay, so that's, you'll have a doubt here when I show on the equation there and here. Okay, so then we substitute the whole thing, substitute for j omega a and j omega b at z is equal to z1. So z1, so if I substitute here, force is equal to z, which is the acoustic impedance, into e raised to minus j k z1. So ultimately we did all this to bring the constants a and b in terms of the velocity, right? The this we had done some substitution before to make this in terms of all the math before we are done. So now we are substituting it back here, jkz1 divided by 2j sin kd minus e raised to jkz1 v2 e raised to minus jkz1 minus v1 e raised to minus jkz2, no sorry, z1 divided by 2j sin kd. Okay, this is the force one. So this is the force on the left side. Okay, so here as we can go back, so if this is the force F1 here, so we wanted to calculate what is the force here and what is the force F2, right? So that is, so here we are able to solve the force here in terms of the velocity and the acoustic impedance, is it? Okay, then so yeah, now we can solve it further to get z into v1 e raised to jkd, d you know is z1 minus z2, no z2 minus z1 minus 2v2 plus v1 e raised to minus jkd divided by 2j sin kd is equal to z into 2v1 cos kd minus 2v2 divided by 2j sin kd is equal to z into v1 divided by j tan kd, is you bring the cos down, get tan, minus v2 by this is just substituting as only, yeah. Similarly, if you solve for z is equal to z2, you will get f2 which is equal to z into v1 divided by j sin kd minus v2 divided by j tan kd. Okay, so then if I So that's how you get that. Then so now I can write, so I'll just write here what is f1 and f2 here explicitly. So here you can write z divided by j sine kd into v1 minus v2 plus j z tan kd by 2 into v1. So how I got this? So here, so this also you can, so this f1 is now in terms of this, so you can make this f1 in terms of v1 minus v2, so and v1. So you can just add more terms. So how do I write? So that you can get from this equation, 1 by tan kd. So that's how you do it. So if I just write it like this, you will not be able to grasp easily. So from this I got it, sin kd plus tan kd by 2. So from this trigonometric identity I can I split it and wrote it so that I can write this f in this form. So why do I need to write this? So here you can think uh, voltage in terms of current. So if I have a, so before I told if the current is branching here, then I will have I1 minus I2. So if, so before I had just shown, so right, so this is expressing in terms of the current voltage as a difference of two voltages. So similarly, before if you are thinking in terms of the current and voltage analogy, you will have I1 minus I2. So I want to write in terms of that. So that's why I have made it. So that's why I have brought this identity and written in terms of V1 minus V2. So similarly, I can write the force F2, which is Z by J sine KD into V1 minus V2 minus J Z tan KD by 2 into V2. Okay. So now I ultimately write the whole equation. So this I can think it of analogy as a voltage V1. This I can analogy I can take as current I2. This is the resistance analogy, resistance. Okay, so if I take that analogy here, so for a force F1 in this direction, I can take this as a resistor. So resistance, what is, so if so this is the current I1, right? This is the current I1, this is the resistance of that region. So J is it tan KD by 2 is the resistance here. J is it tan KD by 2, this is the resistor, and I have the velocity instead of the current I will have the velocity V1 here in the Mason model, and here which is the another resistor I will have here, which is the velocity V1 minus V2. Here is the force I am applying F1 and sum of the velocity. So this is the velocity V2, similar to if you think in terms of current analogy, you will have a I2 here. So yeah, that you can think of similarly. So I can write here, so in terms of F2. So this was my initial model, right? I had two what was it, can look here. So I had a force here, I had a force, I am having a force here. So I'm modeling this part. So when I'm modeling the whole force, I'm applying a force here, getting a force here. So ultimately there are two forces which is producing a wave here ultimately. So there's two forces and a wave in between. So ultimately, so how I can model the whole thing is what I'm showing here. So the both two sides forces come here, this F2 force And similar to the voltage analogy, if you have voltage here, so how do you, so ultimately your voltage drop or your force F is equal to V1 minus V2 into the acoustic impedance term, the resistance, you can call this resistance or acoustic impedance term, into some sine functions. Similarly, you have the current or the velocity here into that resistance. So similarly, the F2 also, F2 side also, you write it like that in terms of these two and P2. So yeah, this is, so what is this? This is minus J Z divided by sine KD. So from here, JZ by sine KD. So yeah, you're just getting this J up, so you're putting a minus here, so you can get like this, minus JZ by sine KD, and this is JZ tan KD by 2 from here, JZ tan KD by 2. Okay, so once you're able to solve, so this minus you can understand, right, from the direction you can understand this is the direction, this is the velocity direction here, this is the velocity direction here. So if we have V2 going here, then this is V1 minus V2 going inside. So ultimately this is the Mason model of the uh, structure we have started initially, where you had two boundary conditions. This is the Mason model ultimately. So here, this I have discussed completely in terms of non-piezoelectric material. So if I have a piezoelectric material, what extra will come is, I'm not explaining too much on that. I'll just show the Mason model, what extra terms will come there. So what I'll have is uh, the resistor here, which is J Z. So for example, if the material, so if I had two, I had shown that the force F1 here and F2 here, and the wave in between, right, incident reflected, so all those things I had shown before, right? So if this material was piezoelectric, okay, then how my Mason model will look is what I'm showing you. Okay, so then here I'll have, so these things are already shown, these three terms you guys already know what is that. So what is extra thing? The extra thing which will come is a transformer. Okay, what piezoelectric does, when you have a force, it will convert that force into a charge, right? So that's what piezoelectric material does. So if I have so that I will need a transformer here. So this is the extra term you will, and this is the in electrical terms. Okay, this is the actual impedance, and this is the capacitance C0, and here I will have the current and a voltage drop which is produced in the piezoelectric material. Okay, so I will have an extra term this because of the, this is from the, because this is a piezoelectric material. Okay, so also if I want to yeah, always you can't just, you will also have a conversion from this. So you'll also have to apply things called piezoelectric transduction equations and stuff when you're converting this to this, and so also those things also come in the picture. So but this is the Mason model if you have a piezoelectric material. And if you are looking at like, for example, I'll just show you how we do it in terms of if you have an actual resonator. For example, if I have a okay, so if I have the actual resonator where I'll have a top electrode. Okay, this is a MEMS resonator. Okay, this will be my piezoelectric material. This will be my bottom electrode, and I will have a substrate. Okay, it's my substrate. So how I'll write a Mason model for this? The Mason model for this will be the first part of the part where I have the top electrode. So that top electrode I'll have to solve it in terms of so impedance of the top electrode. Then there is an effective impedance here. Then I'll have the impedance of the top electrode. So this is the top electrode part. Okay, then for the piezo also I will have a similar thing. We'll have here, so instead here what extra will come, I'll have the electrical conversion thing. So that also the transformer thing I have to put, and I have to write it here. Similarly I'll have here, I'll have a Z0, I'll have a capacitance from the piezo, so that thing will come. So similarly, so these two will be there, and similar thing I will have one for the bottom electrode. So this is the impedance of the bottom electrode, and here I will have this thing, and it will come here like this, and then what this will connect to the substrate. So if I have to write it here, if I can draw it, I'm extending here. So this will be the substrate, same thing, because this is not a piezoelectric material, but there is a strain induced due to the force, and a velocity will be there, and an impedance, acoustic impedance which comes due to the material's acoustic velocity and the density which you can find. So, and then ultimately the substrate also will be there, and ultimately the whole thing will be short to the air. Okay, so be short to air. So here also the top part is also air short. So yeah, this is I'm also given you an example of a of a of an actual piezoelectric resonator, how you model the Mason model. So how you do a Mason model for that. So yeah, this is a basic video on Mason model, which one of my I have got a request in one of my previous video to do a Mason model. So I have covered in detail all the basics what you will be needing to do a Mason model. So yeah, that's all in this video. So so ultimately you understood, right? We have started from here and done the whole Mason model. So yeah, that's all in this video. Yeah, thank you. And if you have any more videos that you want me to do, you can just comment like what Anuj Ashok had done. So that's how I did this video on Mason model. Yeah, thank you. And also please do subscribe if you like the video. That'll be a motivation for me to do more videos.